Welcome to Global Virtual School students. This is your first year chemistry class. I am Dr. Jazbanu, and today is the last lecture of the chapter 2 atomic structure, and the topic for today's discussion is electronic configuration. Students, basically electronic configuration is the distribution of electrons in shells, in subshells and orbitals. How to distribute, where electron will go first, in which shell, in which subshell and in which orbital. This will be discussed today's lecture. And after completing this chapter, this topic electronic configuration, students, you will be able to use the principles like Auf-Bau principle, Pauli exclusion principle and Hund's rule to write the electronic configuration and to distribute the electrons in atoms. And you will be able to describe the orbitals of the atoms in order of their increasing energy levels, which subshell has less energy, which has higher, and how we can calculate, how we can give the order to them in increasing order or decreasing order. Then you will be able to write the electronic configuration of all types of atoms that are given in the periodic table. Students, electronic configuration, we define it as the representation of filling of electron in different orbitals, subshells of an atom is called electronic configuration. And the relative energy of the atomic orbitals increases as like S, P, D, F. S has lower energy than P, P has lower energy than D, and D has lower energy than F. And how we know 1s, 2s, 3p, 4s, 3d, and they have which one has the lower energy? I have a direct simple diagram to understand you how you can find the direct order from this simple diagram. If you understand it, this is very easy and very important. In this way you can directly find out the increasing order of the different subshells according to their energy. And like write this, we have first shell, that is called 1, and we write this is 1s. For second we write it 2s, that contains 2p, and third it contains 3s, 3p and 3d, you know. And for fourth it will be 4s, 4p and 4d, and for it will be 4f, and 5 it will be 5s, 5p, 5d and 5f. Up till now we have maximum learned about S, P, D and F. And for 6 it will be 6s, 6p, 6d and 6f. There is no need to write this 6f. For 7, 7s, 7p, and for 8 just write 8s. For 1, 1s, for 2, 2s, 2p, for 3, 4, 5, 6, 7 and 8. Now cross the orbitals diagonally by arrow. This is the tail and head of the arrow. Again this and this one, then it will be like this one, then it will be like this. This is a direct method to find the order of the increasing energy levels. This one, then like this, and this is like this one. Now start from the tail to head of the arrow and write the sequence of the order of the sequence of the orbitals. Like from this tail to head, here it comes 1s. And then the next tail to head of the arrow, that is 2s. Then in the third one, what comes 2p and 3s, 2p, 3s. And what in the this one, fourth one, 3p, 4s, 3p, 4s. and now in this is 3d 4p, 3d 4p and 5s, and then this one 4d 5p 6s, 4d 5p 6s, and then this one 4f 5d 4f 5d 6p 7s, 6p 7s, and then this one 5f 6d 7p and 8s. So this is increasing energy in this way. This one has the lowest energy 1s, and this end one it has the highest energy. So this is the direct method to arrange the subshells according to their increasing energy level. So 1s has lower energy than 2s, 2s has lower than energy than 2p, 2p has lower than 3s, 3s lower than 3p, and 3p has even lower than 4s. This I will explain you when I will tell you about the n plus L rule. Why 4s is later and 3p is first you have to write, because 4s and this 3d here seems some indifferent thing, but this will be explained in the next slide. So this is very important to understand this diagram, because in this way you find a direct sequence of the increasing energy, and after this you can easily distribute the electrons in these orbitals. That is called the electronic configuration, and that is n plus L rule. And what is the n plus L rule? As you already know that the every orbital has maximum 2 electrons, like s orbital like px, py, pz, and d subshell have 5 orbitals. Each orbital contains maximum 2 electrons. And the energy order of an orbital is governed by n plus L rule. N plus L rule states that an electron will always enter in the orbit having lower n plus L value. For example, 2s and 3d, we have 2 subshells, or you can say the orbitals in different orbits. How to calculate their energy according to n plus L rule? N plus L, apply n plus L. N is the principal quantum number, L is the azimuthal quantum number. For 2s, its principal quantum number is 2 and its azimuthal quantum number s it is 0. So we have the answer 2. And for 3d, it is the principal quantum number 3 plus d s0 p1 d2. So 2. So you got the answer 5. So which has the low n plus L value, that will be of the low energy. Which has the higher n plus L, it will be of high energy. So electron will be filled first in the low energy, that has the low n plus L value, and then it will go to with high n plus L value. Sometimes in this way you have to calculate the n plus L value of all the subshells and orbitals, and then you will arrange them according to the energy. But in the previous diagram, this is the direct way to arrange, to give the sequence of the orbitals as subshells. But sometimes some orbitals they have the same n plus L value. Then what will you do? The electron will fill with first fill with lower n value. Like this, if n plus L values of 2 orbitals are same, then the orbital with lower n value that has lower energy, an electron will be added to that orbital first. For example, 4s and 3p, you have 2 4s and 3p, right? Find out their n plus L value. 4 plus 0, answer is 4, and 3 plus 3p, 3 plus p, for p its L value is 1, so answer is 4. Both have the same n plus L value. So which has the lower n value? Which has the lower n value? Of course 3p has the lower n value, so electron will be first filled in 3p, then it will go to the 4s orbital. And if you find the n plus l values and then according to n you arrange, then you got the same sequence as in previous slide I told you from the diagram. So just remember that, and you can find this sequence, and using this sequence you can fill the electrons. But for filling the electrons, for distributing the electrons, we have some rules that are called the Auf-Bau principle, Pauli exclusion, and Hund's rule. And what is the Auf-Bau principle? It is just like n plus l values. The electrons are placed in energy sublevels in the order of increasing energy values of the sublevels, and according to that you got this the sequence. And second is the Pauli exclusion principle. According to Pauli exclusion principles, no two electrons in the same orbital can have the same set of four quantum numbers. Four quantum numbers: n, it's the principal quantum number, L is azimuthal quantum number, magnetic quantum number m, and spin quantum number s. How? You have the example helium. Its atomic number is 2. So it is 1s2, or you can write in this way 1s, this like this. So it has 2 electrons, and these 2 electrons do not have the same set of 4 quantum number. For example, in this diagram, if we take this one electron, its principal quantum number is 1, that is 1. Its azimuthal quantum number is s, it means 0, and magnetic will be 0. So it will be clockwise or anti-clockwise. Let's suppose this one is the clockwise, and then second will be with n1, l0 again, m0, but now this will be anti-clockwise. So where is the change? This is the change in the spin quantum number. So no two electrons in the same orbital can have the same set of 4 quantum numbers. Similarly, if you have like 2p and 3s, if one electron is here, one is here, then they have n value different. 2 and 3, they have l values different. So there is no two electrons that have the same set of 4 quantum numbers. Somewhere will be difference in like their principal quantum number, maybe in difference in their azimuthal quantum number, maybe they differ in their magnetic quantum number, and maybe they differ in the spin quantum numbers. And last one rule is the Hund's rule. This is also used for the electronic distribution. According to Hund's rule, if degenerate orbitals are available for electrons, the electron would like to live in separate orbital and have same spin like this. This is the same spin. Will be more stable than arrangement like one is empty and one is with paired spin, clockwise and anti-clockwise. This will be explained with this example. Like for example, N7, nitrogen its atomic number is 7, and if we write its electronic configuration, and you know, take the sequence according to Auf-Bau principle, like 1s1, 1s2, 2s2, and now I am expanding the p orbital like 2px, 2py, and 2pz. Total electrons are 7. 2 plus 2 4, and remaining are 3. 1, 2, 3. They have the same spin. According to Hund's rule, they will live in the separate, rather in the same orbital. Like I can write this one: 1s2, 2s2, 2px, 2py, and 2pc. 4, 5, 6, 7, and 8. But this electronic configuration is unstable, because according to Hund's rule, if degenerate orbitals that have of the same energy are available, they will live in the separate orbitals like this one, like this, rather than live like this. One is completely filled, one is half filled, and one is empty. So this is unstable configuration, while this one is the stable electronic configuration. Similarly, for oxygen, its atomic number is 8. 1s2, 2s2, 2px, 2py, and 2pz. 2 plus 2 4, 5, 6, 7, 8. So this is because this one can be in any orbital px, py, pz, but it is not like this 1s2, 2s2, 2px, 2py and 2pz. Its electronic configuration can't be like this 4, 5, 6, 7, 8, because these are the degenerate. This is empty, this is paired, and this one is paired. So this configuration is not a stable configuration, because in this way these are degenerate, one is empty while other is filled. So this will be distributed equally in the orbitals. The left will go, the left one, if there is one more, then that will be paired with any orbital, in any orbital. So this applies the Hund's rule. Hopefully it is clear. Similarly, like neon 10, it will be like 1s2, 2s2, 2p6, that because 6, 7, 8, 9, 10, because this is already a complete electronic configuration. Examples, you have picked the orbital with the lower energy from each of the given pairs. Hopefully students, electronic configuration is clear, and now we will practice with the examples. First of all, pick the with lower energy. This is very simple. I have already calculated for you. Here I am repeating. 3 plus d. For d, L value is SPD 0, 1, 2, and for 4s it's 4 plus 0. 3 and 2 5, and this is 4. So which has the lower energy? Of course this has the lower energy. And for 2p and 3s, 2 plus 1, that gives you 3, and 3 plus 0, it will give you 3. They have the same n plus L value. So orbital with lower n value, which has the lower n value? This one. So this is of lower energy, and in this case this has the lower energy. Similarly, write the electronic configuration of scandium, that has atomic number 21. You have to follow that Auf-Bau principle. That is a complete sequence of increasing energy of the subshells, like this one. So first this sequence will be according to this, then you have to apply all the Pauli exclusion, Hund's rule, and the Auf-Bau principle for filling this. This one 21, you have to write 1s2, 2s2, 2p6, then 3s2, and here it's come 3s, then 3p6 and 4s2, and then 3d. How many? Now first count them. 2 plus 2 4, and 6 10, 11 12, and 6 18, 19 20. So there is left 1, total are 21. So 1 will go in the 3D, because there is 1, I am not expanding it. Otherwise, if you have more than 1, you have to write the dxy, dyz, dxc, and then you have to apply the Hund's rule. First electron will be distributed in all the orbitals. If the left that will paired with any one orbital in the degenerate orbitals. Similarly, like we have the manganese, its atomic number is 25. Now write again, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now 3d5. So I am expanding the dxy, 3d xz, 3d yz, 3d z square, and 3d x square minus y square. So these are the now degenerate orbitals you have. Up till now there are 20 electrons. Now you have 5. According to Hund's rule, they will, if degenerate orbitals are available, they will live in the separate orbitals with the same spin. Rather, you can fill this one here, pair up, single one, but these will be empty. That is not a stable electronic configuration. So according to Hund's rule, they will live in the separate orbital with same spin rather in the same orbital with opposite spin. This is like half arrow. This is not this is like half arrow. You can represent the one electron with half arrow like this. So now you can calculate the you can do the electronic configuration of any or any atom, like if it has the 30 or like is the atomic number 65 or 90, or you can use this sequence and apply this rule. Last one, if it is the P, then expand it. If it is at the last one is the D, then expand it. Then apply the Hund's rule, Pauli exclusion, and all the rules to distribute the electron. So these are questions from your exercise. Why 4s orbital is lower in energy than 3d orbital? It's already I told you about it. Right electronic configuration of manganese I have already done for you. For zinc complete it, and for aluminium you can do the electronic configuration. And practice for more the electrons from the for more atoms from your periodic table. What is n plus n rule? I have already described it. And now you hopefully students, we have obtained all the objectives from this chapter, and after completing all the lectures you will be able to solve the multiple choice questions from the exercise. So you have to do it by yourself, all the multiple choice questions of the exercise chapter number 2. So this was all about the rules, how to fill the electrons, how to distribute the electrons in atoms, and that is called the electronic configuration of elements. And our next topic will be start of the chapter, new chapter, that is chapter 3.